Hey, BC Calc students, this is going to be day 9 notes in your packet. We're going to be talking about differentiability rules today. And these are really some great shortcuts that allow us to find derivatives more efficiently. That being said, just a quick word of caution that if the directions say find the derivative using the limit definition of derivative, then we have to use that limit as h goes to 0 definition. All right. But if we apply that limit as h goes to 0 concept in certain instances, like the derivative of a constant, then we can really find some nice shortcuts. And here's the first rule. If c is a constant, such that f of x equals c, then the derivative equals 0. And if you think of this from a graphical perspective, if you have a constant function, a horizontal line, the slope at any given point along that horizontal line should be 0. So let's actually maybe just prove it quick. The derivative f prime of x would equal the limit as h goes to 0 of f of x plus h minus f of x over h. And since it's a constant function, it doesn't matter if it's f of x plus h or f of x. The output's always going to be that value c. So it's going to be the limit as h goes to 0 of c minus c all over h. And that's just going to be a big old 0 there. So a really quick derivation as to the rule that the derivative of a constant is, in fact, 0. All right, so moving on to the next rule here. The next rule is the derivative of a power function, and this one's super useful and very important. So if you have a power function of the form f of x equals x to the n, where n is some integer, then the derivative would be of this form, n to the x, or n times x to the n minus 1 power. So let's take a quick look then at why this is the derivative using that limit definition again. So given the function x to the n, here's what the original input would be. F prime of x equals the limit as h goes to 0. It would be of x plus h to the n minus x to the n all over h. Now, I believe that last year in pre-calc honors, you do a unit, or at least you have a project that has something to do with binomial expansion. And that's exactly what we're going to do for the quantity x plus h to the n. So maybe you recall what's going on there, but here's what that next step might look like. So when you expand x plus h to the n, it would be x to the n plus the coefficient out front of the next term would be n times x to the n minus 1, and then h there. And what happens is these coefficients are going to change as you go down the line, but the powers of x will decrease and the powers of h will increase, until you eventually get to the last term of that expansion, which is h to the n. So I put a little dots in there to kind of show, depending on what n is, you'll have a bunch of terms. And don't forget about minus x to the n at the end from the original definition, because then what happens is the x to the n's drop out, don't they? And when that happens in this process, we know that everything left over has h in it. So you can take out an h, and that leaves you with n to the x minus 1. But one good area of note here is that every other term that you're left with is definitely going to have an h left over. Right? When I take h from this first term, that's all fine and good, but there's going to be one h left over here, one h here. There's going to be h to the n minus 1 left from h to the n. So when those h's cancel, taking the limit as h goes to 0 makes all of this 0. And notice how I'm left with just n times x to the n minus 1. So that is a quick derivation there of proving if you have x to the n as your function, n times x to the n minus 1 is its derivative. So here's some quick examples of that. If you have y equals x squared, then the derivative is y prime would be 2x to the first, right? If you want to put a power there to make it look and follow the rule there. Okay, and then y equals x cubed, if we have that as our function, y prime would be 3x squared. Okay, kind of drop that power down. X is now raised to the 1 power less. And if we extend that all the way out to y equals x to the 50th power, we would have y prime as 50 times x to the 49th. So I don't know if you learned the power rule in PCH. I feel like when I taught pre-calc honors, I didn't always teach the power rule because I didn't want to give too much away. I didn't want students to kind of start straying away from that limit definition that's also important. But I mean, think about it. If we had to do the definition with something like x to the 50th, you would be expanding x plus h to the 50th. What a nightmare that would be. To, in the end, just know that, oh, wait, it's really just 50x to the 49th. Okay. All right, let's do a few more rules then. So on the next page, we've got rule number 3, the derivative of a constant times a function. If f of x is a differentiable function and c is a constant, okay, such that u of x is equal to the constant times f of x, then essentially, if you find the derivative u prime of x, it's the same thing as that constant times the derivative f prime of x. Let's see if I can focus this real quick. It looks a little blurry. All right, that looks better. All right, so basically a constant times a function is just going to be equal to the constant times the derivative there. All right, so here's a quick example of that. To find u prime of x in this case, it would be the limit as h goes to 0 of c times f of x plus h minus the constant times f of x all over h. And hopefully you're seeing that you can factor that c out. And we know that the limit as h goes to 0 of this expression is just going to be f prime of x. Remember that the limit of a product is equal to the product of the limits. So we can just say that we wind up getting, in the end, pull that c out, right? Limit as h goes to 0 of c is just going to be c times limit as h goes to 0 of this quantity is the definition of derivative. So therefore, u prime of x is equal to the constant times f prime of x. So I think the limit definition really helps us out here to justify these things. And you'll see these types of justifications a lot in this course. You know, it's certainly something that at this level that you're at right now, you can handle justifications and sometimes even proofs that are at this upper level. And I think it's important to do that for us, so we're not just blindly using rules at all times and not seeing why we're allowed to use them. Okay, we won't do for everything, but this lesson filled with a lot of rules for these proofs. Okay, here's an example. If you have u of x equals 3x to the 4th, you can treat the derivative u prime of x as the constant 3 times the derivative of x to the 4th. So the derivative of x to the 4th is 4x cubed. Multiply those constants out front to now get 12x cubed as your final answer. So in a lot of cases, you'll just see that we'll drop the exponent down, multiply it by the constant out front, and reduce the exponent by 1. Okay, so some good rules that we're following so far. What about the derivative of a sum? So if f of x equals u of x plus v of x, where u of x and v of x are both differentiable functions, the derivative of f prime of x would equal the sum of the derivatives u prime of x and v prime of x. So that's kind of nice, right? Just like what we have with this, the sum. The limit of a sum is equal to the sum of the limits. It's really kind of the same idea here with derivatives. So here's what we got in our initial substitution. To find the derivative f prime of x, it would be the limit as h goes to 0 of u of x plus h plus v of x plus h minus the u of x plus v of x all over h. And then from there, we'll kind of group some terms together selectively, right? Put all the u's together, put all the v's together. You can then separate it into two fractions, right? They have the same denominator of h, so that's okay to follow. And again, it's really because the limit of a sum is equal to the sum of the limits that this rule even works. So from here, we can go ahead and say, oh, that's u prime of x, this is v prime of x, and therefore f prime of x equals u prime plus v prime. And then here's an example of that. If you have x to the 5th plus x squared, the way we would find the derivative is just take the derivative of each. 5x to the 4th plus 2x. Of course, if anything's too fast for you to keep up with in the notes today, you guys are going to be pausing as you go along the way. You know, I think now by day 9, hopefully you've gotten used to that. But I think we have maybe just one more rule in today's lesson. We've got one to go. Okay. So for the last rule, we're going to go ahead and take a look at y equals x squared. Oops, sorry. Y equals x squared times x cubed. So I guess the question becomes, for this last rule, is the derivative equal to the product of the derivatives of each? Well, let's actually calculate what that would look like. So the derivative in this case, if I take the derivative of each, would be 2x times 3x squared. So if I apply this rule, it seems like we're going to get 6x cubed. So is that actually the correct derivative? Well, we should know what the derivative is, because really what we're looking at is x squared times x cubed, which is the same thing as y equals x to the 5th power, isn't it? So according to those rules of exponents, now if I find the derivative, y prime, we would get 5x to the 4th, and we're like, oh no. All of a sudden our rules don't work anymore, do they? All right, so here's what I'll say is that clearly in this example, when you find the derivative of a product, it is not equal to the product of the derivatives. Oh no. So the correct answer is in this case 5x to the 4th, but how will I get that using a different rule? So we're going to talk about something called the product rule. And I think we have a proof of this tomorrow, so we'll hang tight on that for now. But the product rule states that if a function y equals the product of two other functions, u times v, then y prime, the derivative, equals the derivative of the first times the second plus the derivative of the second times the first. Okay, not necessarily intuitive, not what we thought according to all the other rules today, just sort of nicely fell into place and made sense until we get to this product rule. Okay, but if y equals u times v, the derivative would be the derivative of the first times the second plus the derivative of the second times the first. So I want you to find the derivative of this function right here using two different methods. So I'll show you what those methods are. Okay. Method one is, let's try and apply this new rule, the product rule. So if I use the product rule, we're going to find the derivative of the first, right? If we think of this as u and this is our v right there, y prime would be the derivative of the first, which actually that's just 2x, right? Derivative of 1, that constant is 0, times the second, x cubed, plus 3x. Plus, now take the derivative of the second, that's going to be 3x squared plus 3, and multiply that by the first, x squared plus 1. So u prime v plus v prime u. We've got it. So then let's combine some like terms, do some distributing here. We're going to get a total of 2x to the 4th plus 6x squared. If I do some FOIL, or I don't know if you guys use box method or anything like that, which would be fine. That's going to be plus another 3x to the 4th plus 3x squared plus another 3x squared plus 3. Okay, I think I've accounted for everything here. Okay, so let's start combining like terms. We got 2x to the 4th and 3x to the 4th for a total of 5x to the 4th. I don't see any cube terms, but we got a couple squared terms. Looks like it's a total of 12x squared. And then we've got plus 3 at the end as a constant. So method one is, let's use the product rule. Why not? We're finding a product. So we can find the derivative using that new rule. So what's method two then? Well, method two is, since this is a product, we can actually pretty easily compute. Let's get this into standard form. We'll multiply it out and then find its derivative. So let's rewrite y as x squared times x cubed, which is x to the 5th. And then I'm going to cheat a little bit and just say, I know there's going to be a plus x cubed in the middle, right, as part of the FOIL here. We're going to get a, from this x squared, oh, I shouldn't have cheated too much. Let's see. It's going to be plus 3x cubed. And then plus 3x at the end. All right, so that's what the FOIL would give us here. Combine like terms to get that y equals x to the 5th plus 4x cubed plus 3x. And now go ahead and just apply that, the fact that we can find the derivative of a sum. It's just the sum of the derivatives. And we're also using that power rule as well. So y prime in this case would be 5x to the 4th plus 12x squared plus 3. And now we're happy because those two methods actually do match in terms of their answers. So product rule is going to be really useful for us, especially if it's maybe not as easy to multiply those functions together, okay, and get a new function that we can find its derivative of. We'll find many other uses that we use the product rule in. And if we've got a product rule, I think we got a quotient rule coming your way too. All right, let me know if you have any questions. Otherwise, we're done for today.